Hello, my name is Oktay. In this video I want to show you two basic principles in organic chemistry, that's functional groups in organic chemistry and conjugated pi electron systems. And this is how it works. Functional groups are like Lego. They are the connection points of these Lego bricks. For example, you got amino group, NH2, OH, hydroxyl group, methyl group, SCH3, aldehyde group, CHO, carboxyl group, or the phenyl group. And there are known reactions, they're called name reactions. And you can use these reactions to build the structures and add functional groups and build bigger structures. And the second principle are conjugated pi electron systems. You got open systems like this molecule 1,3-butadiene, and the number 1 and 3 specify the positions of the double bonds, and you have this phenomenon of mesomeric effect. This means you got sigma bonds, they are localized, but in addition to that, when you have double bonds, you have pi electrons, and all the p orbitals overlap, and you get a delocalization of the pi electrons. The 4 pi electrons can move freely between those 4 carbon atoms. And you can see those two formulas, types of formulas. On the left you have the formula with all the atoms, and on the right you have this formula, simplified formula, but they describe the same molecule 1,3-butadiene. And these open systems are known to have low mesomeric energy. Mesomeric effect is this delocalization of the electrons, and these open systems tend to prefer addition reactions which convert these double bonds to single bonds. For closed systems, you got the Hooker rule. There's a different story. The Hooker rule says if you have 4n plus 2 pi electrons in a cyclic conjugated system, then you get an aromatic system, and those systems have high mesomeric energy, and they don't like addition reactions but prefer substitution reactions. The substitution reaction maintains the cycles, and here you have some examples. You have the cyclopropanium with n it can be 0 in this formula. This is ion, the simplest aromatic compound. Then you got benzene for n equal 1. You got naphthalene and perilene. Perilene is the compound I worked on when I made my PhD. I will show you an example with perilene. And you got other systems too. Those are 4n pi electron systems, and they are less stable. And this is an example. Cyclobutadiene is called anti-aromatic because it has 4n pi electrons. This molecule is not stable. It will rearrange to another molecule. You can't isolate this molecule. And then you got cyclooctatetraene. This is not aromatic nor anti-aromatic, but non-aromatic because it is not flat. The pi electrons pi bonds are isolated from each other. You have no conjugation. And this molecule is more stable. Is shaped like a bathtub. Here you have different formulas for the molecule benzene, C6H6. You have the sum formula, C6H6. You have Kekulé structures. Kekulé was a scientist who researched this molecule and to understand the structure of this molecule. And that's a nice way to say to name this discoveries after the scientists that make them. And this molecule has a planar hexagon structure. The bond length is between the typical length of the carbon single bond and the carbon double bond. On the bottom left you see the sigma bonds. These are from hybridized orbitals sp2. The electrons in these bonds are localized. They can only move in their orbitals. But with the pi electrons, it's different. The pi electrons are made of the remaining p orbitals. They overlap and builds this delocalized pi system. The pi electrons can move freely inside the ring, and this is represented by the simplified formula of benzene. And all bonds in the ring are equal. These are basically 1.5 bonds. Yeah. The ring atoms don't have to be carbon. They can be heteroatoms like nitrogen. And all these molecules are also 6 pi electron systems. For example, pyrrole. Pyrrole has a free electron pair, which is part of the electron system, pi electron system. Whereas pyridine and pyrimidine, they also have free electron pairs, but they are not part of the electron system, pi electron system. Then you get furane, thiophene. Each of the heteroatoms have 2 free electron pairs, one of which is part of the pi electron system, the other is not. Those systems are also 6 pi electron systems, and also all these molecules are aromatic compounds. And the ones with nitrogen are very important because they are used by nature. This example shows this is a formula of the molecule DNA, deoxyribonucleic acid. That's the molecule of life. All life forms have this molecule. And you can see this has 3 components. You got the phosphate groups and the deoxyribose. These 2 components build the backbone of this molecule. Then you got the 4 bases. The 4 bases carry the information, genetic information. And there are 2 pairs of complementary bases. You got adenine and thymine, and you got guanine and cytosine. And you see the dotted lines between these molecules. These are the intermolecular hydrogen bonds. They are essential for the structure of the molecule because they give this molecule the double helix structure. And they have just the right strength. They are strong enough to give this molecule the structure, but they are not too strong. So this molecule can open like a zipper, and you add more bases to this molecule. And at the end, you have the replication process. 1 molecule becomes 2. And you, like I said, you have 4. This is a 4-letter code, A, C, G, T. But there are 21 amino acids. So how does it work? Obviously, 1 letter is not enough. 2 is still not enough. You need 3 bases. Code 1 amino acid, for example, ATG. Adenine, thymine, and guanine are the code for the amino acid L-methionine. This is one important molecule in organic chemistry. Is produced in big amounts. That's aniline. It can be made of benzene. Benzene, you can get it from cracking process of crude oil. First step is nitration. You get nitrobenzene. Second step is reduction with hydrogen. That gives you aniline. And aniline is a very important compound. This can be used for plastic, foam insulation, clothing, rubber additives, herbicides, fungicides, and dye compounds. And I made dye compounds when I was working on my PhD. I will show you an example of these compounds. And you can see the importance of aniline because it has made it into the name of a big German chemical corporation, Badische Anilin Soda Fabrik, BASF. It's a giant corporation with over 111,000 employees. Here you can see one of the organic dye compounds that you can make of aniline. That's called aniline yellow. You can see the principle of a dye compound. You need a big pi electron system. This entire molecule, except the hydrogen atoms, is a big pi electron system. You need a donor group. In this case, it's an amino group. And you need the acceptor group. That's the azo group NN. This is very simple to produce. It's called azo coupling. And the color of these dye molecules depends on various factors, one of which is size of the pi electron system. Second is structure of the molecule. On functional groups, some functional groups move the absorption spectrum to the red, some to the blue. And it depends also on the crystal types. The same compound can, with one crystal type, can be an orange substance, and with another crystal type, it could be a brown substance. This is a historically important compound. Dye compound is indigo. It used to be extracted from plants, so, that's why it was very expensive. This is the structure of the molecule. You can see again the big pi electron system. You got the amino groups. These are the donors. You got the carbonyl groups. These are the acceptors. And this is what it looks like. It's a blue compound. And there was a breakthrough in 1901 when the indigo Pfleger synthesis was invented. It starts with the N-phenylglycine. You make a decyclization using sodium hydroxide, potassium hydroxide, sodium amide. Then you get indoxyl. This compound is not stable in air. It you will get the oxidation, and this gives you indigo. And this allowed industrial mass production, and this compound used for making the blue jeans. Among the dye compounds, there's a subgroup that's called fluorescent dyes, and this Jablonski diagram explains what fluorescence is. You get a dye compound which absorbs light, gets to a higher energy state, then it loses a bit of the energy to non-radiation processes, but most of the radiation it can only get rid of by emitting fluorescent light. And the fluorescent light is always has longer wavelengths than the absorbed light. And for this kind of molecules, you need molecules without rotating parts, because the rotating parts would eat up the energy. This is such one molecule I made when I was working my PhD. It is called NN-bis-4-tritylphenyl-perylene 3,4,9,10-bis dicarboxymide. And this is the structure. You can see the basic structure is perylene, this aromatic compound with 20 pi electrons. This is also the donor group. And this structure, including the perylene and the two dicarboxymide groups, is called chromophore, because it's the structure that gives this molecule its color. And the color is bright red. It's a pigment, and it has a solid state fluorescence. The carboxymide groups are strong electron acceptors. This gives this compound chemical and photochemical stability. And the phenyl groups are spacers. So in this picture, it looks like the molecule is completely flat, but it's not, because you got here a single carbon atom that holds all four phenyl groups. And the angle at this carbon atom is a tetrahedron angle, 109.5 degrees. So these four phenyl groups are more like a propeller, and that makes them spacers, and that gives this compound a solid state fluorescence. And these compounds are known to have a high fluorescence quantum yield. That means a little bit of, if you dissolve a little bit of these compounds, you get a bright, colorful solution. This is how you make this molecule. You start with trityl-aniline. Trityl is this group 3-phenylmethyl. Aniline, you need two of those molecules, and you need one molecule perylene 3,4,9,10 tetracarboxylic dianhydride. And this numbering systems, it starts here in the middle, 1, 2, 3, 4. That's why it's 3, 4, 5, 6, 7, 8, 9, 10. 3, 4, 9, 10. And 4-trityl-aniline is because the atom with the highest atomic number sets the number 1 carbon. That's this carbon that is directly connected to nitrogen. 1, 2, 3, 4. The carbon opposite of it is number 4. That's why 4. Yeah, that's how you make it. You have 85% yield, which is good. Yeah. This is what it looks like. This is an example. You can see. The big surface is not as bright as the edges of this molecule, of this piece of plastic, and this plastic contains just a few milligrams of this compound. And this is one of the applications of this molecule. It's a light collector. You imagine if you had a big piece like this, a big plate, and you could use this as a light collector. You could place solar cells along these edges and use them more efficiently. And second, application is rapid fluorescence antibody tests. Antibodies are made of amino acids. They have also functional groups like amino group or carboxyl group. And you can connect these dye molecules to these amino acids and print it on paper. That gives you an antibody test, quick antibody test for dangerous diseases like HIV or corona. And a third application is fluorescence marking. This is important for recycling. We live in an era of climate crisis, energy crisis, but also resource crisis. And one solution is, of course, recycling, more recycling. And you could use these compounds to dye expensive sorts of plastics. And this will allow you to automate recycling. And for this to work, very little amount of these compounds is sufficient because machines have can detect much lower concentrations than the human eye. Yeah. This is a typical technique that's used in dye chemistry. That's called thin layer chromatogram. This is how it works. You have a beaker, glass beaker. You fill it 1 centimeter high with chloroform or ethanol, and you have this paper, special coated paper, is coated with silica gel. And you take one tiny drop of your mixture, reaction mixture, drop it on at about 1.5 centimeter distance from the edge, and then you put the paper into this beaker, cover the beaker, wait about 7 minutes. The solvent will slowly creep up this paper, and the different components will be dragged along at different speeds. And this is how you find out if your reaction has worked or not. And I've made over 100 of those chromatograms. Yeah, and it's an efficient method to find out if your reaction was successful or not. This is what a PhD looks like in Germany. It's made of thin cardboard material. This is the upper part of the document. The lower part contains personal information like birth date and things. And my colleague made a funny comment. He said this feels like it was cut out of a cornflakes package. Yeah, and I got this for 20 new compounds that I made. My original plan was to make fluorescent dye molecules, but in the end only half of these molecules were fluorescent molecules. The other half were non-fluorescent molecules, normal dye molecules. And the interesting thing is the scientifically most valuable molecules were among this second group of non-fluorescent groups, because most of these compounds had a functional group. Then this group was an amino group, and this means you can use these compounds for further reactions. For example, you can build new rings. Yeah, and I made 20 of those compounds in different structures, different colors: yellow, orange, red, purple, blue, and yeah, that's how I've done it. This is what's most important about going to university, in my opinion. The most valuable lessons have nothing to do with chemistry. It's what's called soft skills. For example, time management, communication skills, organization skills, teamwork. Teamwork super important. I had great mentors and colleagues that helped me a lot. I'm very grateful for that. And at the university, this is a bit stressful and a bit competitive environment, and you learn a lot about people. And that's a great experience, and you become a more mature person. It's a very, very good thing. And you learn also about how to prioritize different things, analytical thinking, effort, discipline. And one lesson I learned is, I call it power of little things. What I mean by that is I had more than a dozen. I had about 15 concepts of making new compounds. None of them worked. They looked all very good on paper, very promising, but they did not work. And then I made a tiny modification. Switched from element that's called in Germany natrium, that's sodium. I switched from sodium to lithium, and that was it. And that was the key. And that 4 months later, I had 20 new compounds. It was a great experience. This is how my interest in science started. In Germany, it's called Bücherbus. This was best day of the week was Wednesday. When this bus came, you could lend books for free for 2 weeks. And I especially liked Enid Blyton adventure books and documentations about animals. That was the first time when I came in contact with the scientific principle. And when I was in 3rd grade, I got the Meyer-Sand lexicon, which is an encyclopedia. I read everything. And yeah, we must understand there are still today 2.9 billion people. They have no connection to internet. Imagine how the world would look like if they had also had something like Bücherbus. And education is a very powerful tool for good. And I really admire people who are working on projects like Wikipedia or One Laptop Per Child, because that makes a huge difference. And yeah, that's very important. And learning is a lifelong process. You never finished, and this really very nice thing. This is my best game at chess.com. I like to play against Isabel. Isabel is a chessbot with ELO 1600. That's about medium strength. And I have only a 10% success rate. I'm just a beginner. And you can see the best piece is a b4 pawn. It blocks the black queen from the crucial square f8, right? And there are 2 components to intelligence. In my opinion, one is overrated, the other is underrated. There's the problem-solving part, problem-solving intelligence, which can be measured by the IQ test. And this is, in my opinion, overrated. Of course, you have an advantage when you have above average IQ, but there's more, and the second part is at least equally important. That's emotional intelligence and empathy, which is, in my opinion, underrated. This is about trying to understand how other people feel and think, and try to get along with other people. And it's, of course, it's not always easy. Sometimes, yeah, the bad situations. But yeah, this is equally important. And in my opinion, the combination of these 2 factors is what makes a difference. This is a typical thing in science. Many scientists, when they study this phenomena in nature, they get an understanding of the beauty of nature. And nature is very complex, but at the same time, it's very simple principles. And yeah, that makes you really appreciate the beauty of nature, and we must do more to protect nature. Yeah, that's what I also learned and understood when I was studying chemistry. And I will, in the future, I will make more videos about chemistry, and I will focus on theory, because that's why what I was interested in the most. And my next video will be about this tiny molecule. It is everywhere around us. It is in our body, and this molecule is, of course, water. So thank you for watching. Have a nice day. Bye bye.